Uh, is this clear? Okay.
Yes, can see.
So let's start right now.
Yes. We start now, and then I think it's 3:05 to 3:35, and then we have a half an hour. Yeah.
Okay, no problem. So my name is Sarison. You can just call me Cyrus. And I'm from the mathematical physics group of the School of Math and Science at UniMel. It's really a great pleasure to speak here. And I'm also like to give my special thanks to Siyu, to Douglas, and to Yang for their invitation and organization. And today I'm going to talk about the representation theory of a homogeneous Gaussian unitary, and which is a direct continuation of the previous work done by my principal supervisor, Dr. Lucas Hacker, where they solved the so-called homogeneous Gaussian unitary, the homogeneous case. And I would also like to say that I believe this topic does not have that much strong connection to integrability and geometry, but it's definitely be within the large picture because it has some really strong connection to quantum computing, especially for the quantum optics and some mathematical physics, the groups. Okay, so what I'm talking about today, well, there's one key concept I need to introduce, that is the family of Gaussian unitary transformation, and that these are characterized by the property that the map Gaussian states to Gaussian states. And what the Gaussian state, they are a special type, a special family of quantum states of a Gaussian form, and they have been used in quantum optics and also in condensed matter physics. And what you need to know is that the family of Gaussian unitaries, well, Gaussian unitary is a short for Gaussian unitary transformation. They are generated by two subsets, namely squeezing and displacement. And what has been solved in here in the background is only the squeezing part. And to clarify the reason why we call them squeezing, we just mean they are the operators quadratic in annihilation and creation operators, and because they can also be kind of, because they are rank 2 operator, they can also be, order 2 operator, they also be seen for like squeezing after some change of basis in the classical phase space. And now in this work, we also include the displacements, creating the full group of a homogeneous Gaussian unitary, which means we have both squeezing and displacement. And the full group is relevant in various applications where you describe continuous variable quantum computing, of course, as quantum information, as well as optical system, but also, for example, the other areas like using cold atoms with bosons. Okay, now let me introduce you some formulas I'm going to use. So we are looking at a quantum system of n bosonic degree of freedom. So now we are just focusing on the bosonic system. You can think of it like n harmonic oscillators, and the classical system and its classical system is characterized by canonical conjugate variables, which are n position operators and n momenta. Where the position the q's and momentum is the q. And we collect them into a single operator valued vector to psi, well, with two n indices, the first n at position, the last n momenta, and it is also known as a quadrature operator. Now, once we have the symbol, what we call psi, we can then write down Hamiltonian. When we're here, if you can see, I'm not sure if I have, where's my laser? Is this laser? sorry, I don't think I have the laser. Do I have the laser? No, I don't have the laser. Okay, that's fine. I can just read the equation. So we use Einstein summation convention, and so here HAB here is a matrix, and it's times two of the times the two cosine vector, and F is a vector, C is just scalar. And this is the most general quadratic Hamiltonian we can write down that with both the quadratic and the linear part with the scalar part. But we all know that a scalar just rescaling of the energy and the constant shift is not something really interesting. And now we can finally introduce the most important concept. Let's start from Gaussian state also haven't been introduced formally. Whenever a quadratic Hamiltonian has a unique ground state, that is a Gaussian state. And Gaussian unitary, as already foreshadowed, they are exactly the unitary transformations generated by the exponential of quadratic Hamiltonian. Well, the general quadratic Hamiltonian will create both the displacement and the squeezing, because as you see, it has both quadratic part and the linear part. And the other type, what we call homogeneous Gaussian unitary, they are generated by the quadratic part only. So you can also imagine that the homogeneous Gaussian unitary, they are just the squeezing only case. And now, but what we are really interested in is the homogeneous case, which is the full story that we really want to solve. And the subtlety here, also for the whole work, is we would like to figure out what is the correct overreaching complex phase. Because if you, let's say, first of all, we would like to define what is really meant by complex phase. It's something that the phase, the overall angle with respect to the Gaussian state with J. And so it's just a complex number on the unit circle. And there's a very important motivation why we need to care about this phase. Well, the first motivation is that the description by just a squeezing matrix that represents the squeezing is a matrix, and displacement vector, well, it is vector in the phase space, will only determine our homogeneous Gaussian unitary up to complex phase, which only a complete story. And for example, in the previous work, which we only have squeezing part, this complex phase is just plus minus one. And this angle, what we call phi j, is the handle to reach a unique description. Now we have an additional phase on this matrix and vector. And we also would like to care about the actual phase difference between the two Gaussian unitary, U1 and U2. This is the case when we multiply two a homogeneous Gaussian unitary with each other. And the other case is, I would say that such a problem is not a big deal in many situations, because, for example, if you just evolve a Gaussian state with a Gaussian unitary, the overall complex phase of the unitary is just the global phase, and a global phase is not physical, it's not really something we care about. However, there are some situations, for example, superposition of Gaussian states. For example, you have two Gaussian states, a U1 of J and J, there are two Gaussian states, and now you added them together and adding with another Gaussian unitary U2, and now it's no longer a global phase that you can ignore, because now it's a relative phase between two states, and rather than just a non-physical global phase. And that is why actually in many situations, tracking the phase is non-trivial. Okay, now I'm going to give you some beautiful illustration of what's meant by a Gaussian state by their so-called Wigner quasi-probability distribution. In the first picture, you just have a perfectly circled Gaussian state here. It's a 3D plot, and the the x and y coordinate just a regular position q and momentum p. So that's the first one. And then if you apply a squeezing on it, it will well literally squeeze, as you see on this 3D plot. And moreover, you can also apply a displacement, which again literally displace the whole distribution, displace the center of the distribution. And what this illustration is for only for a single degree of freedom. However, just for a higher dimensional space, it's just similar thing. And for this 1 degree freedom, just to give you the idea in this particular case. And I'm also going to present it from the above because now you can see clearly how the family of Gaussian sets, namely squeezing and displacement, acting on Gaussian sets, and how they squeeze the shape on the second plot and displace the center of the distribution on the third plot. Okay. Okay, now we have some mathematical formalism, which I should say is also including the Fermi-Ardi case. So as previously we said, the purely quadratic Hamiltonian is referred to if you have linear term of zero, and they have some beautiful mathematical structure related to representation of Lie algebra and Lie groups. So the Hamiltonian themselves is a formal representation of Lie algebra. What it's supposed to be is that Gaussian unitary generated by the exponential should form the Lie group corresponding to them. However, in reality, in the physical world, they actually generated the double cover rather than the actual Lie group. So for bosonic system, it's symplectic algebra, symplectic group. For fermions, it's special orthogonal algebra and group, but it can also be orthogonal. We actually saw for the orthogonal case, but the special orthogonal case is more clear for everyone to understand. Of course, moreover, we're now focusing on the Fermi-Ardi case. So their double covers are the metapolitic for bosons, a spin, or pin group for fermions. Well, these are the cases if you just stick into the purely quadratic case. However, if you would like to track the phase, there will be a problem because, for example, in the previous what it showed for the metapolitic group. Why? Because for the metapolitic group, the well representation is it's infinite dimensional because there's a theorem says that there could not be a faithful but finite dimensional representation for the metapolitic group. And their solution is by giving a parameterization other than a representation that can uniquely categorize all group elements, which means you now at least now it's computable, and to show you here how they solve the problem, give you some illustration. So if you see the green circle here is a the simple formula we have, which is the case, you can imagine they are a symplectic group. And the red spiral, they are the double cover, which is a metapolitic group. So there are always two elements in the double cover corresponding to one in the symplectic group, and we don't know which corresponds to what. So their solution is given by the parameterization, where they have another psi, it's another phase, it's a complex number on the unit circle. And if you see on the right-hand side, the cylinders and the disk, you can see, well, they're the same one, but just viewing from different side, that it is the blue dashed lines, it's the U1 group. So it's just a phase, and now we use the phase to coordinate which is which. So now you don't have to solve in the infinite dimensional you don't have to deal with infinite dimensional matrices, but you can only to deal with a finite dimensional symplectic group, as well as for its glue it to a U1 phase. Now you can use the U1 to determine which is which if the element is double covered. And here's the key. The second key is now we can extend everything to the homogeneous Gaussian unitary. And the first line, second line, but the second line is just the same Hamiltonian, most general quadratic Hamiltonian. And now we would like to make a decomposition. As you see the first line, we would like to decompose the Gaussian unitary, the homogeneous Gaussian unitary, into a EI theta, which is the overall complex space with with the formula, and the DZ is the displacement operator, and squeezing. The final one is the squeezing operator, and introduced before, which has been fully characterized in the previous work. So the other thing is the homogeneous Gaussian unitary. It is characterized by the following condition. First of all, as you can see, if you have two inhomogeneous Gaussian unitary, if you apply them onto a phase space vector, which we use psi, it will generate a squeezing matrix MAB times this vector. So it will squeeze it first, and then with a plus of z, so that is a displacement. That is exactly the reason why we say MAB is a squeezing matrix, and z is the displacement vector. And if you notice in the first line, now if you just apply them, the phase, the overall phase, which is the capital psi, they will cancel. They will not appear in the physical sense in this problem. However, we still have to count it for some reason, as we said before, and we can, and we successfully did that. If you see the next one, it's the multiplication law. Sorry, the multiplication laws. If you multiply to Gaussian unitary. Well, the first two, if you see the M1, M2, they just combine together, and Z1, Z2, this Z1 plus M1, Z2. This is when you decompose the Gaussian unitary, you swap the one displacement and one squeezing, and it will creating the squeezing of the displacement. But the key part is the final entry. As you see, the psi 1, psi 2 times e to the zeta. Well, zeta function is the key of it's one of the main result of this research. As you see, it is something really long. But the key message you should take from this slide is that we can now describe the zeta function in terms of different pieces that essentially relates to rewriting or decomposing and decomposing the parts of the displacement and squeezing. And now we have the last one is we have now the fully analytical closed formula that keeps track of this phase. So with that, we have not only a parameterization of the homogeneous Gaussian unitary, but we also know exactly their multiplication laws. While obviously this formula looks like complicated, of course, but these are finite dimensional matrices. You can just put them on a computer, so you don't need to know exactly what they are. You just need to provide the basic, like the M1, M2, Z1, Z2, and they will automatically give you everything. And you can read our papers if you want to understand them in detail. But the critical the achievements is it's now easy to implement. You don't need to deal with the infinite dimensional matrices. You just need to deal with the finite dimensional matrices, and the standard operations that you can do with Mathematica and the other programming languages. You can just put them inside it, which makes everything simpler. Well, that is one of our key results. And the other thing is, I'd like to give you a little demonstration of why our formula is correct. So in general, we can plot the complex phase, which is given by the formula on the last line, as a function of t. So now we can do a time evolution for randomly generated quadratic Hamiltonian. So here the orange line, the orange solid line represents our analytical formula of theta t, which is generated before, and the dashed line, they are the truncation approximation for different truncated Hilbert space. So truncation, because as we said before, the Hilbert space is infinite-dimensional, so we can't really do it on computer. That is a problem, right? So for this case, we do a truncation, which means we cut off some certain level of the harmonic oscillator, and n is how much we cut. So in general, the most accurate case should be for n, this n max equals to infinity. And so with higher number will be more accurate, with less level of truncation, for example, n equals to 30, where it will have much larger sensitivity. And it can also be represented by the first plot. If you see the green dashed line, they deviate first, and then a higher precise one, the crayon one, deviate finally the blue one. So, but at least as our expected, the first part they matched exactly. And the other case is for another type of generated. Well, not I should not say they are another type. They have some special property that they really close to the identity. So for somehow the randomly generated Hamiltonian, their time of evolution were just around identity. So if you see now, we only need n equals 30, which is the not so accurate one in the first plot, to match exactly for everywhere as t is evolved. And this example shows that at least for some specific case, our analytic formula match the numerical simulation exactly. Well, for some cases, but for the other cases, still match if you see the first few seconds, no seconds, let's say t in the first part. So it definitely meets our expectation, and so the analytic formula is correct. And the other thing I would like to say is the algebra property of our generated group. So because we still would like to say what is the resulting group, or at least a set. So for the bosonic system, the displacement operator, they form a Heisenberg group of dimension 2 and plus 1. I would say that this sentence is not so accurate, because in fact, the displacement operator, it has a unitary just circled on it. So it's not something really accurate. However, the Heisenberg group, it could be imagined as a universal cover of this bosonic displacement group, but it's not really big deal. Let's say it's a semi-direct product of the metaphysitic group with the Heisenberg group. So it's a result like the formal like that. It's what we call a homogeneous metaphysitic group. Well, however, as you say before, if you see the formula for zeta is really complicated. So it is something really say it's a twisted product, and here it really means that the homogeneous metaphysitic group is a central U1 extension of the homogeneous symplectic group. So it's something more complicated. Now you cannot say simply like a Cartesian product or semi-direct product. Well, for the fermionic case, because we haven't introduced them formally, because for the fermionic case, they have some Grassmann property with all the its parameters are Grassmann valued, and that will be a problem, because the displacement operators, they will map the fermionic Gaussian states outside the physical Hilbert space, and so they will not associate with any physical observables eventually, and that is why we ignore them in this case, and because they are physical, so undetectable, but their mathematical formalism is still interesting. So if you read our paper, we have some analysis for the fermionic case for their mathematical structure. And finally, let me give you final case study that because previously we just said that what is Gaussian unitary and we were dealing with the general Gaussian unitary now. So if we have a time-independent Poisson general quadratic Hamiltonian in this form, what is the corresponding Gaussian unitary? What is the corresponding group parameters? So that it is. So the unitary parameters, what we say, the m, z, and psi, corresponding to the squeezing matrix, displacement vector, and the complex phase, corresponding to the quadratic matrix. Well, yeah, the quadratic parameter HAB is matrix, FA vector C a constant, as the following. So they are some direct result from the BCH, from the Baker, Hostam, Campbell. Yes, there's that formula, a really famous formula in the algebra with this final result. Well, yeah, that it is, which means give you any randomly generated quadratic Hamiltonian, you could always transfer them using these formulas into a Gaussian unitary. And with this formula, because we have got m, z, and psi, you can definitely track the phase, like here, as well as the multiplication law. And I believe that is kind of the end of my talk. And I believe we can have more deeper understanding of the topic. For example, what is the Gaussian state? Mathematically, it's the unique ground state of quadratic Hamiltonian. And if you do exponential for quadratic Hamiltonian, you got something map a Gaussian state to Gaussian state, what we call a Gaussian unitary transformation. And it has two tabs, one squeezing, one displacement. The previous research has fully solved the squeezing part with some beautiful Lie algebra and some double covers. Now we add the displacement to the system and complete the story. And finally, it may have some applications in continuous variable quantum information, quantum optics, and even finally in some actual optical devices. And that it is. Any questions?
Thank you, Cyrus. Are there any questions from the audience? If not, I have a question. So could you please go back to the your analytical formula and this graph here.
Okay.
I think it's the next page. Yeah.
This one?
Yeah, so my understanding is your analytical formula is obtained by the parameterization and the dotted lines are simulations.
Yes, they are simulations, and they are the formula because let me be more clear, because if you see the line on the top, they are some multiplication. So we can still do the same thing for the resulting unitary, and we can still compute its complex phase using for truncated, well, for the truncated case. Because as you see, maybe before, let's go back to before. There, yes. Here, the definition in the red block is say this with respect to some Gaussian state J. And in reality, such a J is infinite dimensional vector, right? So if you want to really to do that, because the operator A is also infinite dimensional matrix, so you can't really compute it. However, we can always compute them if we shorten the J, shorten the A into some finite dimensional matrices, some finite dimensional vectors. Well, in Mathematica, you just the ground state is just 1 0 0 0 0, and for example, the cat 30 is with 30 0 and 1 1. So if we can always truncate it, and we can use them to do everything else and to compute the phase from before and after. and then we can divide them to see what is really the phase difference and to draw these dashed lines.
I see. And for the second graph,
Mhm.
it looks like there are some fluctuations. It's not really periodic, but it looks somehow
Yes, there are some
periodist.
theoretical property because, as I said, so we haven't done a fully analysis for this random. Well, it's also randomly generated, but we haven't done a fully analysis. So the intuition is, it is something that both of the generated result, they both really close to the identity. And when do a time evolution, both of them will just go around because that is the identity of the group. In terms of geometry, they will just go around through somehow of the identity. So if you see the green line, they will also there's also close, very close when the phase small, which means um, there are still well, of course, because truncation of tens really small and will create a very large acidity. However, it can still be really, really close um, because the overall is close to the identity.
I see. I see. Yeah. Thank you for the answer. Are there any further questions from the audience? If not, let's thank the speaker again. And now we have a 30 minutes break from now, which means the next session will start at 4:07. Yes. Thank you guys. See you at
Thank
4:07.
you for the opportunity for explanation.
Thank you, Cyrus.